Hi, Ramisa. I've got the video that I sent you. I've got a picture from it on the screen here because I thought that would be a good place to start. And I think that maybe just in your understanding of it, I can see from working with you last Thursday that you have a really good understanding of all of the calculus concepts that you've learned and that you learn quickly. So I think maybe you might just be trying to make this a little harder than it is. It's just, I think it's just the concept of like, why do we jump in and start doing all this and what's the purpose for it that you're having a hard time with. So if I can try to understand that a little bit better, it might help, I'm hoping. And if not, email me back. We'll keep plugging away at this until we get it sorted out. So for the graph 1 over x squared, this is the graph that he provided. So we'll work from there. And this is similar to the one in your textbook also. Basically, the test for the convergence is a really simple test in this case. If the sum of the terms is going to be what they're calling bounded by a real number. In other words, we know that the sum can never, it's an infinite sum, right? So we know that we can never arrive on like a final answer, like boom, there, got it, that's the answer. It's always going to be plus that little bit more, plus that little bit more, plus that little bit more. So basically what we're saying is when we're asking for the sum of the bounded terms, what we're really saying is what's the limit of the sum of the terms. And we don't even need to go that far. We don't even have to know exactly what the limiting value is. All we have to do is prove that it's real. So if it doesn't go to infinity, it's real. And those are our only two choices. So this whole test, this whole integral test, is built around the idea that when we have a curve such as this one, y equals 1 over x squared, we know that we can find the complete area under the curve, the total area under the curve, using the integral to find area under the curve. And I know you've done that in your course previously. That will actually give us the exact area under the curve. So what we're doing is calculating that, but then having to say, but we know that's not equal to the area of, or the sum of all of these terms, because the sum is infinite and we could never get a number for that. And so I think that's the confusing part in all of this for you, is just to realize that the reason we have to do this, we can't just find the integral and say, aha, there's the area under the curve. It's equal to 2, so therefore it's a convergent series. It's that less than bit that they keep putting in there. And so basically all they're saying with the less than bit is that the sum of all of our terms is always going to be less than the integral of the function, because the integral is the exact sum for that function, the exact area under the curve, whereas this is only a partial sum because we can always add on one more, right? So this one will always be a little bit smaller than this one. But if we can find the integral and get a value for it, that's when we can go, aha, it's real. We have a real number. And that's all we need to say, therefore, it converges. And so that's what Sal is doing, is just finding the integral of this. And on Thursday night, we sorted out that the first part of finding the integral, so that you can use it as a definite integral and actually calculate the area, is to find f of 1, because that's an easy one to figure out, right, with the length of 1. You just substitute 1 in to the formula 1 over x squared. And then the other part of it is the rest of the area under the curve, which has to be the integral from 1 to infinity. And we can't integrate from 0 to infinity. So from 1 to infinity, we're going to integrate that curve and get the rest of the area. And in this case, that turns out to be 1, or has a limiting value of 1 anyways, when you substitute infinity in to the antiderivative. And so by getting 1 plus 1, we can go back here now and we can say, therefore, the sum of the partial terms is always going to be less than 1, because with the partial terms, there's always one more we can add. So we haven't arrived at the total yet, but we know we're not going to be able to go over 2 with our total, because that's definitely the total area under this curve. That's what they mean by the sum of terms is bounded by. It just means that there's an upper limit, a number that we're never going to reach, but we can see it in the distance, just like a limit. We're getting there. We're getting there. Our answers are 1.999999999, but we're not getting to 2 because we never will. And so that's what they mean by that upper limit being bounded. And so it's a lot of complicated calculus talk for really just saying, if you can take the value of the function at x equals 1, evaluate the integral over 1 to infinity, and get any real value, any number at all, other than infinity, then your series converges. If not, it diverges. And that's it. That's the entire test. And as you saw when we were doing it together on Thursday night, sometimes they make the integrals really hard because the test itself is really easy. So I hope that helps. But if not, email me back, and we'll keep going with this until you have a really solid understanding of it. But maybe just let go a little bit of, the thought that it's a difficult and complicated thing, because it's actually not. It's really just that simple.